This video will illustrate the concept of forward and backward propagation in neural networks. Let's assume we have a data set about hungry people. We have a variable in the data set that contains choices of things to eat. We want to build a neural network to predict this dependent variable. We also have a variable in the data set that contains the time of day. This independent variable may predict the kind of food a person will choose to eat. If the time is 8 a.m., a bowl of cereal is a likely food choice. The pathway from the 8 a.m. independent variable value to the bowl of cereal dependent variable value is known as forward propagation. The more records in the dataset that show an input of 8 a.m. leading to an output of bowl of cereal, the stronger this forward propagated relationship will be in the neural network. Similarly, if the independent variable is 12 noon, a likely dependent variable value is sandwich. More 12 noon inputs will strengthen the forward propagated relationship between 12 noon and sandwich. We can also backwards propagate to build the neural network. If the food choice in the dependent variable is pizza, a likely independent variable value is 5 p.m. Neural networks are strongest when they use both forward and backward propagation to identify the most common paths between independent variable inputs and dependent variable outcomes. Of course, not every record will have the same output from a specific input. It is possible, even likely, that a person who is hungry at noon will choose pizza rather than a sandwich. Because of variation which will occur naturally in the dataset used to train the neural network, it is necessary to trace the connections between the dependent variable values and the independent variable values forward and backward. The more a connection is found in the data, the stronger the connection becomes, enabling the neural network to improve its ability to predict when it sees a pattern it recognizes. The area between the independent and dependent variables through which the arrows pass is known as the hidden layer. This example has compared a single independent variable containing only 3 possible values, 8 a.m., 12 noon, and 5 p.m., to a dependent variable containing only 3 possible outcomes, sandwich, pizza, and bowl of cereal. Imagine if your data set had more independent variables, maybe 8 or 10 or more. The crisscross of pathways through the hidden layer would quickly become extraordinarily complex. Despite this complexity, computers are able to forward and backward propagate tens of thousands of pathways every second in order to build neural networks that can reliably predict the dependent variable outcomes from the independent variable inputs. Whether a data set is small like the one in this example or very large, this process of forward and backward propagation remains the same and is the building block for predictive analytics in neural networks.